It is 44 degrees outside. Your ceiling fan is just moving hot air around. Your electricity bill last month was enough to make you wince. And the worst part? The people who built homes in this landscape 1,000 years ago were not sweating like this. They did not have air conditioning. They did not have electricity. But they had something we have almost completely forgotten how to build. Two things, actually. A mud chimney that acts like a giant exhaust pipe for hot air, and a crawlspace tunnel that pulls cool earth air directly into the room. Together, these two features can drop the interior temperature of a mud hut by anywhere from 8 to 15 degrees Celsius compared to outside. Verified, measurable, reproducible. Today, we are going to build both, step by step, mud in our hands. I will explain why it works, and how you can replicate it with materials available almost anywhere on Earth. No power tools required, no cement required, no money, really. And at the end, I want to answer the question that has been bothering me since I first learned about this. Why did the modern world forget it? Before we touch the mud, you need to understand three things. Because if you understand the physics, you can adapt this build to any climate, any structure, any material. The first principle is this: hot air rises. Always. This is called the stack effect, or thermal buoyancy. Hot air is less dense than cool air, so it naturally rises. In a sealed room, hot air accumulates near the ceiling, radiates heat back down, and raises the overall temperature of the space. It has nowhere to go. The mud chimney gives it somewhere to go. It creates a dedicated exit point, positioned high in the wall or through the roof, through which that hot, buoyant air continuously escapes. The moment hot air leaves, it creates a low-pressure void that pulls in cooler air from below. This is not mechanical. It is physics doing exactly what physics does. The second principle is this: the Earth is a thermal battery. At the surface, the ground heats up and cools down with the seasons and with the sun. But just 1.5 meters to 2 meters underground, roughly the depth of a crouching human, the temperature stabilizes. The Earth at that depth in most regions sits between 14 and 22 degrees Celsius, year-round, regardless of what is happening above. This is why caves are cool in summer and warm in winter. Not magic, just thermal mass. The Earth absorbs and stores temperature slowly, and at depth, seasonal extremes are completely smoothed out. The crawlspace tunnel exploits exactly this. Air enters the tunnel at ground level, travels through a passage buried 1 meter or more below grade, and arrives in the room pre-cooled by the earth it traveled through. The longer the tunnel, the more earth contact, and the cooler the air delivered. The third principle is this: moving air feels cooler than still air. Even if the air entering through your crawlspace tunnel is only 4 or 5 degrees cooler than room temperature, a constant gentle movement of air dramatically improves thermal comfort. Evaporative cooling from your skin means that moving air at 28 degrees can feel more comfortable than still air at 25 degrees. When you combine the stack effect with underground pre-cooled air, you create a continuous, self-sustaining circulation loop with no moving parts, no electricity, and no maintenance. These three principles are the entire basis of the build. Everything we do from here on is just applying them with mud, straw, stone, and patience. Now let us talk about what you actually need. For the mud mix, you need clay-rich subsoil, not topsoil. Topsoil is full of organic matter and will crack and decompose. Dig down at least 30 centimeters past the topsoil to find the dense yellowish or reddish clay layer. Do a simple field test. Take a handful, dampen it, and roll it into a snake. If it holds a snake 20 centimeters long without cracking, you have workable clay. You need coarse river sand, not fine beach sand. Sand is the anti-shrink agent. Clay shrinks as it dries. Sand prevents that shrinkage from cracking your work. A rough mix ratio that works for structural mud walls is 70% clay soil to 30% sand by volume. You need straw or dried grass fiber. This is your tensile reinforcement, the same role steel rebar plays in concrete. Cut it into 10 to 15 centimeter lengths. Mix it into your mud at roughly 1 double handful per bucket of mix. The straw binds the material together and distributes tensile stress so your chimney walls do not fracture from wind vibration or thermal cycling. You need water. Clean water. Add it slowly. The mud mix should be stiff enough to hold its shape when pressed, not flowing like soup. For the crawlspace tunnel, you need a digging tool, a mattock, a pick, or a sturdy spade. You need wooden or bamboo poles for the tunnel ceiling. You need flat stones or fired brick for lining the tunnel floor so it does not erode. Gravel also works. Optional but recommended. Terracotta drainage pipe sections, 20 to 30 centimeters in diameter, if available locally. These can be laid end to end through the tunnel and make the build faster and more durable, particularly in high rainfall climates where bare earth tunnels can collapse. You also need two thermometers, one for inside the structure and one for outside, so you can record the temperature differential once the system is running. Before you touch a shovel, you must read your site correctly. Two decisions made here will determine whether this system works brilliantly or fails completely. The first decision is to orient the tunnel inlet toward the prevailing wind. Walk around your structure in the morning, at midday, and in the late afternoon. Note which direction the wind tends to come from. In most regions, there is a dominant prevailing wind direction, especially in summer. You want the tunnel inlet to face into this wind. The wind will naturally push air into the tunnel, supplementing the stack effect suction from the chimney. Mark this direction and drive a stake at the point where the tunnel will enter the ground. The second decision is to check the depth to stable soil. Push a long metal rod into the ground about 2 to 3 meters from your inlet stake. You want to confirm you can dig to at least 1.2 meters depth before hitting rock or standing water. In most earthen construction climates, this depth is easily achievable. If you hit rock at 60 centimeters, you will need to angle the tunnel deeper at the far end or line the entire tunnel route with terracotta pipe. The minimum effective tunnel length is 4 meters. Below 4 meters, the air does not spend enough time in contact with the cool earth. Between 6 and 10 meters, you see the most dramatic cooling per meter of additional length. Beyond 10 to 12 meters, the gains diminish because airflow velocity drops due to friction with the tunnel walls. For a first build, target 6 to 8 meters total length. Mark out your full tunnel route with stakes and a string line before you dig a single spade of earth. Now we build the tunnel. The chimney comes second. Always build the inlet before you build the outlet. Step 1. Excavate the trench. Dig a trench 60 centimeters wide and at least 1 meter deep along your marked route. At the inlet end, the end that will be above ground, dig at a 30-degree downward angle for the first meter. This angled entry prevents rainwater from flowing directly into the tunnel and increases the Venturi effect as wind accelerates through the narrowing angle. Brace this section with flat stones on each side as you dig. From the angled entry, level out the floor of the trench and continue horizontally. Maintain a minimum of 1 meter depth from the trench floor to the surface for the full run. This is your thermal cooling depth. Step 2. Line the tunnel floor. Before you roof the trench, line the floor with flat stones, fired brick, or compacted gravel. This prevents erosion from airflow and keeps moisture from saturating the air passing through. A bare earth floor will work, but will degrade over time. Step 3. Install the tunnel ceiling using the formwork method. This is the most critical structural step. Cut wooden poles or split bamboo to span the width of your trench, roughly 80 to 90 centimeters long, for a 60 centimeter wide trench with wall support on each side. Lay these poles transversely across the trench at 30 centimeter intervals for the full length of the tunnel. Over the poles, apply 2 layers of your mud straw mix. First layer, 5 centimeters thick, pushed firmly between the poles and packed tightly. Allow this to stiffen for at least 4 hours in direct sun before applying the second layer. Second layer, another 5 centimeters covering the tops of the poles. Total ceiling thickness is approximately 15 centimeters including the poles. After the ceiling has dried for 24 hours, cover it with a minimum 30 centimeters of compacted earth. This burial layer provides the thermal mass that cools the air inside the tunnel. Do not skip it. The ceiling alone will not provide meaningful cooling. The buried earth above the tunnel is the active cooling medium. Check your dimensions at this point. The tunnel interior should be 60 centimeters wide and approximately 50 to 60 centimeters tall from floor to ceiling. This gives adequate cross-sectional area for airflow. If you are using terracotta pipe instead of open trench, lay 3 20-centimeter pipes side by side in the trench to achieve equivalent cross-section. Step 4. Build the tunnel inlet screen and cap. At the above-ground inlet end, build a low mud brick surround that rises 30 centimeters above ground level. This prevents surface water, debris, and animals from entering the tunnel. The open face should be oriented toward the prevailing wind. Cover the opening with a coarse wire mesh or tightly woven bamboo screen, mesh opening no larger than 1 centimeter, to exclude insects and rodents while maintaining airflow. Step 5. Connect the tunnel to the hut. The tunnel's terminal end passes through the hut wall at or just below floor level. Frame this opening with flat stones or fired brick to prevent the wall material from eroding at the junction. The interior outlet must be at floor level, never at mid-wall or high. Hot air is already near the ceiling. You want the cool incoming air to enter low and displace it upward and out through the chimney. If the outlet is positioned high, you short-circuit the airflow loop. Install a sliding wooden cover or a hinged mud flap at the interior outlet. This allows you to fully close the tunnel on cold nights, during dust storms, or when the system is not needed. With the tunnel complete, we now build the chimney. Hot air, being lighter, rises. The chimney gives it a path to escape the building. As it exits, it creates negative pressure at ceiling level inside the room, which draws the cool tunnel air upward from the floor. The loop becomes self-sustaining as long as there is a temperature differential, which there will be whenever outside is hotter than the tunnel air. Step 1. Choose the chimney location and type. There are two effective configurations. Configuration A is the through-roof chimney, a vertical mud shaft that rises from ceiling level through the roof and terminates above the roofline. This is the most effective configuration for maximum draft. The taller the chimney above the roof, the stronger the thermal buoyancy effect. Configuration B is the high wall vent chimney, a horizontal or angled vent channel built into the upper section of the wall, at least 80% of the wall height, that exits through the wall face. This is simpler to build and requires no penetration of the roof. For first-time builders, Configuration B is recommended. Configuration A delivers significantly stronger performance but requires careful waterproofing of the roof penetration. We will build Configuration A here, as it is more instructive and more powerful. Step 2. Mark the chimney opening in the ceiling. Mark a 30 by 30 centimeter square opening at the highest point of your ceiling. In a conical or domed mud structure, this is at the apex. In a flat or gently sloped roof, choose the highest corner or ridgeline. Cut or chip out this opening carefully. Frame it with 4 flat stones or fired bricks as a collar. This collar prevents the surrounding material from crumbling into the chimney opening over time. Step 3. Mix the chimney mud. For the chimney walls, use a slightly stiffer mix than for general wall construction. Increase the sand ratio to 60% clay, 40% sand by volume. Add straw fiber as before. Test your mix with the drop test. Pick up a tennis ball-sized lump, hold it at shoulder height, and drop it on a flat surface. It should flatten without spreading more than 2 to 3 times its original diameter. If it spreads further, add more clay. If it barely spreads, add more water. Step 4. Build the chimney shaft using the coil method. Roll your mud mix into coils approximately 4 centimeters in diameter and 40 to 60 centimeters long. Begin building the chimney shaft by laying coils around the perimeter of your framed roof opening, pressing each coil firmly onto the one below it and smoothing the joints so there are no air gaps. Each complete ring of coils is one course. Build 3 to 4 courses, roughly 15 to 20 centimeters, then stop and allow the completed courses to stiffen for 2 hours before continuing. Mud walls built too quickly will slump under their own weight before they can dry. Patience here is not optional. For a chimney of 80 centimeters to 1 meter above the roofline, you will need approximately 10 to 12 building sessions, spaced 1.5 to 2 hours apart. Plan this over 2 to 3 days. The interior cross-section of the chimney shaft must maintain 20 by 20 centimeters minimum for the full height. A smaller interior dimension significantly reduces draft velocity. Step 5. Build the chimney cap. This step is often omitted and causes chimney failure in the first rainy season. Cap the chimney with a flat stone or fired terracotta tile, approximately 40 by 40 centimeters, suspended 10 to 12 centimeters above the chimney opening on 4 small mud pillars, 1 at each corner. The gap between the stone and the top of the chimney shaft is open on all 4 sides to allow air to escape freely, but rainwater cannot fall vertically into the shaft. Apply a waterproofing render to the exterior of the chimney shaft above the roofline. The best traditional render is a mix of cow dung, clay, and water in roughly equal parts. The organic acids in cow dung create a hydrophobic surface layer when dried. Lime render is equally effective if available. Step 6. Seal the roof junction. Apply a generous fillet of mud render around the full perimeter of the base of the chimney where it exits the roof, sloping outward away from the chimney to shed water. Apply your waterproof render over this fillet. Allow 48 hours of dry weather after construction before testing in rain. The tunnel is complete. The chimney is complete. Now we verify that the system functions as a connected loop. Open the interior tunnel outlet at floor level. Open the chimney cap if you installed a temporary cover during construction. Wait 20 to 30 minutes with all windows and doors closed except for the tunnel inlet and chimney outlet. What you are looking for is a measurable and continuing drop in interior temperature relative to exterior. The system does not cool instantly. It takes 20 to 40 minutes for the airflow loop to establish fully and for the thermal mass of the walls and floor to begin responding.